Welcome to your deep dive. This time,
Yeah.
we're tackling Einstein's theories of relativity.
Wow.
And you've provided us with
Yeah,
some
yeah.
incredible stuff.
Some really heady stuff.
Excerpts from Einstein's own writings.
Yeah.
So
It's amazing.
get ready to unpack how this one guy revolutionized our understanding of
Go.
space-time
Yeah.
and the entire universe.
It's going straight to the source.
Yeah.
You know, experiencing his thought process.
Exactly.
Yeah.
And he starts off by laying a pretty crucial foundation.
Uh-huh.
This idea of a reference frame.
Right.
He uses the example of a man walking on a train to show how motion is relative.
Yeah. And I think that example is so brilliant because it's something we've all experienced.
Right?
Imagine you're on that train, you're strolling down the aisle.
Okay.
To you, your path is a straight line.
Yeah.
But to someone watching from the platform, you're moving in a curve along with the train.
So even something as basic as whether you're walking in a straight line or not depends entirely on where the observer is standing.
Exactly.
It's like those optical illusions
Yeah.
where the same image can look like two totally different things.
Exactly. And Einstein takes this seemingly simple observation and shows how it completely changes how we measure the universe.
Yeah.
He really emphasizes how even measuring the distance between 2 points relies on your reference frame.
And that's where things start to get really interesting, right?
Why?
Because this whole idea of a reference frame sets the stage for him to completely upend our understanding of space and time with his special theory of relativity.
You got it.
Okay.
Before Einstein, everyone pretty much took for granted that time and space were these absolutes,
Yeah.
ticking away at the same rate for everyone, everywhere.
Right.
But Einstein comes along and says, like,
Okay.
hold my beer.
And cue the mind-blowing thought experiments.
Exactly.
Right.
This is where Einstein really shines. He asks us to imagine a beam of light traveling inside a moving train.
Okay.
It sounds simple enough, right?
Yeah.
But it leads to some wild conclusions.
Okay, bear with me here, because I remember this one from physics class, and it still makes my head spin a little.
Okay. Yeah.
So imagine you're on that train again,
Okay.
and you shine a flashlight down the aisle.
Okay.
Now, the speed of light is constant, right?
Right. That's one of the fundamental laws of physics.
But the train is also moving.
Right.
So if you're standing on the platform watching this, shouldn't the light from the flashlight be traveling at the speed of light plus the speed of the train?
That's what common sense would tell us. But Einstein realized that if the speed of light is truly constant,
Yeah.
which experiments were showing,
Huh?
then something else has to give. And that something is our traditional understanding of time.
Whoa. Okay, so you're saying that to make the speed of light constant for everyone,
Yeah.
regardless of their motion,
Uh-huh.
time itself has to be relative.
You're getting it.
Whoa.
For someone on the train, time would pass normally.
Oh.
But for someone standing on the platform, watching the train zoom by, time on the train would appear to be moving slower.
Wow.
It's called time dilation.
So time isn't this universal metronome
Yeah.
ticking away at the same rate for everyone.
Yep.
It's actually more like stretchy,
Yeah,
flexible.
exactly.
Yeah.
And it's not just time.
What else?
Length gets distorted too, which Einstein called length contraction.
Wow.
The faster an object moves, the shorter it appears in the direction of its motion from a stationary observer's perspective.
So wait, if I'm picturing this right,
Mm-hmm.
you're telling me that a spaceship, for example, traveling at a significant fraction of the speed of light would actually appear shorter to someone back on Earth.
Precisely.
And that
Yeah.
time inside the spaceship would be moving slower relative to time on Earth.
It's enough to make your head spin, right?
Yeah.
But the thing about Einstein's theories is they're not just some wild thought experiment.
Mm,
These effects are actually measurable.
right. Like that whole thing with GPS satellites having to account for time dilation to make sure our directions are accurate. That always blows my mind.
Right.
It's like relativity isn't just some abstract concept.
Yeah.
It's literally built into the technology we use every day.
Exactly. And it's these kinds of connections to the real world that make this whole deep dive so fascinating.
Right.
But hold on tight,
Okay.
because it gets even weirder when we start talking about gravity.
Okay. Bring on the weirdness. I'm ready. What does gravity have to do with all of this?
Well, this is where Einstein's general theory of relativity comes into play.
Okay.
And it all starts with this idea called the equivalence principle.
Okay.
Have you ever been in an elevator and felt that brief sensation of weightlessness as it starts to go down, or
Mhm.
that feeling of being pushed into the floor as it accelerates upwards.
Oh, absolutely. It's like that
Yes.
roller coaster feeling,
Yeah.
but in an elevator.
Exactly.
Yeah.
Einstein's genius was in realizing that that feeling, that sensation of acceleration, is indistinguishable from the feeling of gravity.
Hold on. Are you saying that being in a gravitational field is the same as accelerating through space?
In a way, yes.
Wow.
And to illustrate this, he uses the example of a rotating disk.
Like a giant spinning merry-go-round.
Exactly.
Okay.
Imagine you're standing on the edge of this spinning disk. You would feel a force pushing you outwards.
Yeah, like you're about to be flung off.
Right.
Okay.
And Einstein showed that this outward force, what you feel as you're flung away from the center of the disk, it's indistinguishable from gravity.
Wait, so you're telling me that spinning around can create a force that feels like gravity,
Yeah.
even if there's no massive object like the Earth pulling you down?
You got it.
Wow.
And this led Einstein to a truly groundbreaking realization. Gravity isn't a force in the traditional sense, like magnetism or the strong nuclear force. It's actually a curvature in the very fabric of space-time itself.
Okay, time for another visual aid. Is it safe to say my brain just broke a little? Space-time is like a giant trampoline, and massive objects like planets and stars are like bowling balls, creating dips in that trampoline.
That's a great analogy.
Okay.
So instead of thinking of the Earth pulling you down with a mysterious force, think of it more like the Earth warping space-time around it. And you're just following the curve.
Whoa, so when I'm sitting here, I'm not just sitting on a chair. I'm also surfing a space-time wave created by the Earth.
You could put it that way. And here's where things get really cosmic.
Yeah.
Einstein realized that if gravity warps space-time locally, as in around planets and stars, it must also warp space-time on the scale of the entire universe.
Which brings us to the cosmological problem, right?
Yeah.
Trying to figure out the shape and size of the entire universe. That's a pretty big question to tackle. What was Einstein's take on that?
Well, he realized that the traditional Newtonian view of an infinite static universe just didn't add up. It led to some pretty significant problems, like the one Seeliger pointed out, which essentially said that if the universe were infinite and filled with stars, the night sky should be blindingly bright.
Wait, why wouldn't it be? I've never thought about that.
Think about it this way. In an infinite universe, every single point in the sky, no matter how small, would eventually intersect with the surface of a star.
Okay.
So the night sky should be blazing with starlight, yet it's not.
Okay, I can see how that's a bit of a problem. So how did Einstein resolve this?
Wow. He proposed a truly mind-bending solution, a finite but unbounded universe.
Okay, hold on. How can something be finite but also unbounded? That sounds like a paradox.
It does, doesn't it?
Yeah.
But imagine the surface of a sphere, like a globe.
Okay.
You can keep traveling in one direction on the surface of that globe forever, and
Right.
you'll never hit a wall or an edge, right?
Right.
But the surface of a sphere also has a finite area. You could measure it if you had a big enough tape measure.
Are you saying that the universe could be like a three-dimensional version of a sphere?
Yeah.
Okay.
If we hopped in a spaceship and traveled in a straight line for long enough, we'd eventually end up back where we started.
Wow.
That's one possibility,
Okay.
and it's a consequence of curved space-time.
Wow. That's incredible.
It's enough to make anyone question everything they thought they knew about reality.
Oh, yeah.
But here's the thing. It's not just some crazy idea.
Right.
Einstein's theory actually makes testable predictions.
Okay, that's what I want to know. How do you even begin to test something as mind-boggling as general relativity?
Well, one of the first pieces of evidence came from an unlikely source, the planet Mercury.
Okay.
See, astronomers had noticed a slight wobble in Mercury's orbit that Newtonian physics couldn't quite explain.
So Newton's laws worked great for most of the planets, but Mercury was like, nope, not playing by your rules.
Exactly.
Uh-huh.
But when Einstein applied his theory of general relativity, it perfectly predicted the wobble in Mercury's orbit.
Wow.
It was a huge victory for his theory. And then there was the 1919 solar eclipse.
Oh, I think I read about this. Wasn't that the one where they measured the bending of starlight?
You got it.
Okay.
See, Einstein predicted that the sun's gravity would be strong enough to actually bend the path of light coming from distant stars.
Okay.
And during the 1919 eclipse, when the moon blocked out the sun's light, astronomers were able to observe and measure the exact amount of bending.
Wow.
And guess what?
It matched Einstein's predictions.
Exactly.
Wow.
It was a stunning confirmation of his theory and made him a global celebrity practically overnight.
So if I'm trying to like wrap my head around all of this,
Yeah.
Einstein used
Yeah.
a wobbly planet and
Yeah.
some bent starlight to prove that gravity isn't even a force. It's all about warped spacetime.
You got it.
Oh, yeah.
And he didn't stop there.
Oh, no.
Remember earlier we were talking about time dilation and special relativity?
Yeah.
Well, general relativity takes it a step further
Okay.
and says that gravity also affects the passage of time.
So it's not enough that time is relative to your motion.
Hmm.
Now it's also being messed with by gravity.
Yeah.
How does that work?
Essentially, the stronger the gravitational field, the slower time runs.
Oh.
So time on the surface of the Earth, for example, actually runs a tiny bit slower than time out in deep space, far away from any massive objects.
So you're telling me that if I wanted to slow down my aging, I should just go live at the bottom of the Grand Canyon?
Theoretically, yes.
Uh-huh.
Though the difference would be so incredibly small you'd need an atomic clock to even measure it.
Right.
But it's a fun thought experiment, isn't it?
Yeah, it really is.
Yeah.
Okay, so we've got gravity warping spacetime, time being relative. How in the world did anyone even begin to try to put all of this into a mathematical framework? It makes my head spin just thinking about it.
Right. That's where Hermann Minkowski comes in.
Okay.
He was a mathematician who looked at Einstein's special relativity and realized that it could be described much more elegantly if you considered time as a fourth dimension.
Fourth dimension. Okay, I'm officially lost now. I can barely visualize 3 dimensions, let alone 4.
I know, it's a tough one to wrap your head around.
Right.
But essentially, Minkowski said that instead of thinking of space and time as separate entities, we should think of them as a part of this unified fabric called space-time.
Okay.
And this four-dimensional space-time is the backdrop against which all of the universe's drama unfolds.
So it's like space and time are intertwined, woven together into this 4-dimensional tapestry.
Right.
That's wild.
It is wild. And it turns out this four-dimensional framework wasn't just some mathematical trick.
Boy.
It provided the necessary tools to develop the mathematics of general relativity, allowing physicists to describe gravity as a curvature in this four-dimensional space-time.
So Minkowski was like, hey, Einstein, I think I found the perfect mathematical language to describe your crazy universe.
Exactly. And it
Okay.
revolutionized the field of physics.
Yeah.
Suddenly, gravity wasn't just a force acting across empty space.
Right.
It was a fundamental property of the universe woven into the very fabric of existence.
You know, it's something to learn about Einstein's theories in a textbook.
Yeah.
But going this deep,
Yeah.
hearing about the thought experiments,
Mhm.
the historical context, it really brings it all to life.
It really does. And I
Yeah.
think that's the beauty of going straight to the source, reading Einstein's own words.
Right.
You get a glimpse into his genius, his ability to ask the really big questions,
Right.
and then have the audacity to actually try to answer them.
And for me, one of the biggest takeaways from all of this is the sheer scale of Einstein's thinking. Like, he wasn't just tinkering around the edges of Newtonian physics. He was proposing a radical new way of understanding reality itself.
Right.
And it all started with a simple question. What does it really mean for something to be in motion?
And that's what makes his work so endlessly fascinating.
Right.
Einstein's theories weren't the end of the story. They were just the beginning.
Yeah.
They opened up a whole new frontier of scientific inquiry, from the study of black holes and the Big Bang to the search for a unified theory of everything.
It really makes you wonder what Einstein would make of it all if he could see how far we've come and how much his work continues to shape our understanding of the universe.
Yeah.
What do you think? What rabbit holes are you going to go down next after this deep dive?
Well, I don't know about you, but I'm feeling a sudden urge to brush up on my tensor calculus.
Uh-huh. Yeah. I might just stick to staring up at the night sky and contemplating the vastness of it all for a while. What about you listening? Has this sparked any questions or ideas you'd like to explore? Because that's the whole point, right? To keep questioning, keep exploring, keep diving deeper into the mysteries of the universe. Thanks for joining us on this incredible journey into Einstein's mind. And until next time, happy exploring.